Well, we'll start with nano, nanoelectronics and nanotechnology in construction materials. Okay, there are two things. Okay, nanoelectronics is slightly different, and nanotechnology in construction materials is different. Okay, unit 5 contains these two things. Okay, so we'll start with switching glasses. Okay, what are these switching glasses? So you might have heard about green buildings, where whenever you want light, just make the glass transparent and get more light. Whenever you don't want light, you make it tinted, okay, colored glass, so that less light enters the room or the building. Okay, so this technology is known as switching glasses, and there are various methods of making these switching glasses, okay, or chromic glasses we say. So what we study here is basically electrochromic glass only. For your syllabus, I just kept electrochromic glasses. There are various techniques. By heating, you can change the color. By uh, different radiations. Okay, upon instead of light radiation, it may change the color. Okay, in the night it becomes transparent. Okay, there are so many things, okay, of making switching glasses. Switching glasses means the glass becomes transparent or colored, bleaching effect and coloring effect. Okay, so what we do nowadays, whenever you want, okay, awning means you just have canopy or kind of thing, so that inside, okay, there is no much heat. Okay, during summers, okay, we use these kind of things, right? So inside it is cooling effect will be there, or we use blinds, okay, vertical blinds or horizontal blinds, so that whenever we don't want light, we can just close these blinds. Okay, whenever we want light, we open this. You might have seen these things, awning and blinds. So electrochromic windows or switching glasses, this is bleaching state. So bleaching state means light is entering inside. Here you don't want light, so it is reflected back. Okay, so he just wants to control the light, how much light he wants for his work, right? So we don't have to use electric bulbs and all those things, right? On state and off state. Okay, when you don't want, keep it off so that light directly enters. When you want light to be controlled, on state. Okay, so you can use electricity. Okay, I mean small, one. If you apply 1.5 volt to tungsten oxide, nickel oxide, right? I'll discuss how it is constructed and all. Okay, it's based on nanotechnology. Okay, so what are these smart windows? Today, it is desirable to regulate the solar radiation, sunlight. Okay, what is the wavelength of sunlight? It starts from 300 nanometer. That is what you call UV A radiation. We say 400 nanometer is visible, up to 700 visible light. UVA visible light. Then 3000 nanometer is nothing but infrared light. So thermal radiation, heat. Okay, infrared. Okay. So we get all these three lights, light radiation from sunlight. Okay, solar radiation consists of UVA, visible, and infrared light. Okay, through our windows. Okay, and we want to regulate it. Whenever we don't want light, sunlight, we just have to stop it. Okay, during summer season, we don't want sunlight to enter. Okay, during winter season, we want to keep the inside, the heat. We want to heat the inside building. Inside, okay, all right. The At the same time, let as much as possible the sunlight should enter. Okay, the building through the windows in the winter. In the summer, we often prefer to shut off but a bit of sunlight, sun radiation. Okay, sunlight or sun radiation. Countries with large climate and temperature variations, especially European countries, where you in summer temperature goes to 40 degrees Celsius, in winter it goes to -5 or -10 degrees Celsius. Okay, so variation is more. When you go to northern part of India, also the climate variation is more. Here we don't have that much change in climate. Okay, all the time, the temperature will be around 20 to 25. 99% of the time, 25 to 20 to 30 degrees Celsius only. Only 10 to 15 degree variation will be there in our part. But when you go to north or when you go to south, okay, in Australia and all, in Europe, okay, in Canada, the temperature variation will be huge. Okay, -40 to +40 in Canada. Okay, so very drastic changes. Okay, that time you need to control the sunlight. Okay, during winter we want more sunlight to hit us. Okay, heat the building. Okay, during summer, okay, right. We don't want the light to enter. We want to protect ourselves from the sunlight. So, right, we want to keep ourselves cool. So, reject all the most of the sunlight. Okay. So, expenses for heating and cooling will then be reduced. Okay. This we don't do in India, especially we do only cooling. Okay. Summer season, we use ACs and air conditioners or air coolers or something. But heating usually we don't do. Okay, 99% we don't do it. Okay, during winter we do it, but not much. But in Europe, without heating, if it is one day the heating is not on, people will die because of that cold. It's so much cold. Okay, so it can be reduced. Okay, awnings, canopies, or blinds could become superfluous. Means redundant. We don't have to use them. Applications of awnings and blinds are more or less static. Okay, so just once you use awnings, okay, what happens? You have to remove. Means it takes really long time. Okay, they're static. They are always there. Okay, blinds, they'll be there always. Okay, and in most cases, not operated efficiently. Every day we have to open it, close it, or whatever it is. So to do all those things. Okay, so it is then desirable to use more flexible arrangement. Just like when you switch on the fan or something, you just press the button. So when you press the button, the color of the window changes. It becomes transparent. Suddenly it becomes colored. Okay, you don't have to do anything. Okay, it's a flexible arrangement which can regulate the energy transfer through the windows to much larger extent. An automatic control will often be preferable based on a temperature sensor. You can use temperature sensor. Okay, if you feel you set the temperature. Okay, if the temperature is more than 25 degrees Celsius, just switch off. Okay, switch on that. The color should be colored. Okay, then if the light is more, okay, the temperature is less. We want more light to enter, then we can just automatically it should switch on. Okay, temperature sensor, it is attached to the switch. Okay, you don't have to regulate, means on, right, using buttons, right, it automatically regulates itself. Okay, light sensors or temperature sensors, if you use, you can regulate the switching glasses or electrochemical windows. Okay, once you program it, everything happens automatically. Okay, right. Control of energy transfer through windows is important in connection with the energy economizing. Okay. The basic property of an electro switching, okay, optical switching, okay, optical switching material or smart windows or switching glasses or electrochemical windows, whatever it is that it show a large change in optical properties. The optical properties of this glass, switching glass, changes drastically upon changing either light intensity or spectral composition or heat. If you heat it, its color changes, or electric field or injected charge. So basically, we study here electric field. Okay, we apply voltage and we get the different colored glass. This optical change results in the transformation from highly transmitting state to partly reflecting or absorbing state, either totally or partly over the solar spectrum. Okay, sometimes you want light and you don't want the heat. So at that time, what it has to do, it has to reflect only the thermal radiation, infrared light, not the visible light. Sometimes you want light and you right, you don't want, sorry, sometimes you want heat but not the light. That time it should reject only UV and visible light, not the infrared light. Is that clear to you? So it's very tricky. Okay, so people are developing new kind of right switching glasses. Okay, one or two examples I'll discuss in the coming slides. The physical phenomena of interest, okay, for optical switching processes can be classified in one of the two categories. There are two categories of switching glasses. One is discrete mass movement that includes ion or localized electron motion, okay, as seen in photorefractive, photochromic, electrochromic, and thermochromic materials. Okay, in these materials, electron transfer or ion transfer happens. So because of that, what happens? The color of the material changes. Discrete mass transport, we say, or mass movement. Or sometimes the mechanism may be collective physical movement that includes dispersed homogeneous liquid crystals. Okay, we can use liquid crystals. Okay, between two glasses, in between that we use liquid crystals or suspended particles, deformable membranes. Okay, and adjustable diffraction gratings. Okay, so when you use deformable membranes, okay, they can be moved, right, up and down. Okay, so membranes will be like this. Okay, this is glass, another glass. Okay, membranes will be here. Okay, these are the membranes. One membrane, another membrane, third membrane, fourth membrane, another right. It is on state, so light is transmitted. Okay, we want light inside. Okay, it's not switched on, so it's off state side. Okay, light is entering now. What I'll do now, I'll switch on it. When I switch on it, the membrane will be blocking the light. Another membrane blocking the light. Third membrane. This is between two glass layers. Okay, membranes may block the light or may transmit the light. Okay, or liquid crystals may orient in a particular direction where it allows light. Okay, it may orient in other way, right, and may block the light. Okay, so collective movement it is, collective movement. And discrete movement means electron transfer happens. That's it. Electron transfer or ion transfer happens. Okay, that happens in photorefractive, photochromic, electrochromic, and thermochromic materials. And for your syllabus, I'm just keeping this to electrochromic because if I discuss everything, it becomes a big topic and it's very difficult for you to write in the examination also. Okay, I'm just keeping only restricting myself to electrochromic windows. Okay, all these processes are classified as chromogenic. So they generate color, chromogenic. Electrochromic windows or switching glasses. How they are constructed? Solid-state electrochromic devices contain cathodic and anodic electrochromic materials. What they contain? They contain cathodic and anodic electrochromic materials, okay, that are separated by a solid state hydrated electrolyte selected from the group of tantalum oxide, antimony oxide, lithium niobate, etc. These are used as electrolytes. Okay. This structure is sandwiched between indium doped tin oxide electrodes. What is indium doped tin oxide? Indium doped tin oxide is it's also known as TCO. What is TCO? Transparent conducting oxide. Indium tin oxide, okay, indium doped tin oxide is conducting, okay. It is called transparent, transparent, okay, then metal oxide or conducting oxide, conducting oxide. Okay, TCO. Okay, usually we use FTOs or ITOs. FTO means fluorine doped tin oxide. I told you how to make one tin oxide. Tin oxide is SnO2. Tin oxide is nothing but SnO2. Okay, it may be FSnO2 or ISNO2. Indium doped iron SNO2. Either it is FTO we call or ITO, tin oxide. Okay. How to make it? I told you, just you take a glass. I have a question. Just tell me the answer, anyone. Okay. I'll take a glass. Okay. I'll cut the glass into two. Okay. On one glass, I'll just apply some oil, or all right. What I'll do, I'll just tarnish it with my bare hands. Okay. Then I'll use a light, okay, say 100-watt bulb. I'll keep a detector on the back side, okay, just to monitor how much light is coming. Okay, same thing here. This is pure glass, and this is tarnished one, tarnished glass. Tarnished glass, okay, okay, right. So this is case one and this is case two. Tell me in which case light transmitted is more. Case 1, tarnished glass or pure glass. I am just passing 100-watt light through these glasses. The same glasses, one I have tarnished with my bare hands. Okay, I'm just keeping the same detector here. Okay, which detector sees more light? Pure
Case
glass
2.
or yes?
Case 2,
One clear.
sir.
Case 2. Anybody else? You can type it in the if you want. Case 1 or case 2. No answers. Only one student answered it. That case 2 means pure glass transmits more light. Anybody else? Yes? Tarnished glass or pure glass? Which transmits more light? reflection, refraction, all these things you have studied, no? In PUC physics, reflection of light, rarer medium to denser medium. Okay, what happens? Reflection happens, refraction happens, right? See,
Yes,
more light is observed in tarnished glass. Why? Because this is the glass. What is the refractive index of glass? Ri 1.5. Refractive index means what? What is what do you mean by refractive index of glass is 1.5? What is the refractive index of air? 1, right? So when light travels from 1 refractive index to 1.5, okay, what is the refractive index of diamond? Ri of diamond? Anyone? This 2.3, right? Ruby and diamond 2.5, 2.3 to 2.5. Okay. Higher the refractive index, what happens? More reflection. Rarer medium to denser medium, more reflection. What it indicates? Ri 1.5, the velocity of light is 1.5 times less compared to velocity of light in the vacuum. Okay, refractive index is what? Velocity of light in the vacuum divided by velocity of light in the medium. Medium always the velocity is less. Okay, so that because of this refractive index, it undergoes reflection, refraction, and all those things, right? So in tarnished glass, what is happening now? Tarnished, I have tarnished it, right? Here refractive index is 1 in air, and it is 1.5 in the glass, right? The tarnished oil layer, it is 1.25. So less bending happens first, 1.25. So light enters, okay, small refraction, then it enters. Reflection will be less here. Okay, that is the reason, right? You use if somebody uses spectacles, okay, it is coated with what? Anti-reflective coatings. What are they? Their refractive index is in between air and glass. Okay, I think I discussed this in during solar cells. Okay, to collect more light, we coat it with anti-reflective coatings. Anti-reflective coatings allow more light to reach the right solar, right, this one. Okay, so here, okay, why I'm discussing all these things, just we require some coatings and all. Okay, that I'll discuss in the next class anyway, but I'll just remove all these things first. Okay, to darken or color the windows, a voltage is applied across the two transparent conducting layers, oxide layers. Okay, this voltage drives the ions from ion storage layer through the ion conducting layer into the electrochromic layer. So how it happens, I'll discuss in the next slides. Okay. So to reverse the process, voltage is reversed now. Okay, driving the ions in the opposite direction out of the electrochromic layer through the ion conducting layer, okay, into ion storage layer. As the ions migrate out of electrochromic layer, it lightens, or we call it as bleaching effect. The window becomes transparent again. Okay, this system comprises of whatever the electrochromic windows or the switching glasses, right? It contains what? A glass, okay, two glasses, okay. Inside they are coated with what? ITO. Okay. They have mentioned adhesive film. It doesn't matter. Just to attach this film to glass. Okay. Then we require nickel oxide nanoparticles or nickel oxide layer thin film. Okay. And this side tungsten oxide thin film. Inorganic electrolyte, say titanium oxide, or I discussed earlier mentioned lithium niobate, antimony oxide. They are used here as electrolyte. Okay, so glass on both sides. Okay, coated inside with conducting material, thin layer of ITO, indium doped tin oxide, nickel oxide. Okay, as anode, tungsten oxide as cathode. Okay, inorganic electrolyte, right? Tantalum oxide is used as inorganic electrolyte. So this is a construction. There's no, it's not a big deal. Okay, just this is, these two are glasses. Okay, inside it is coated with what? It is coated with thin layer of ITO. Okay, 0.2 micrometer ITO. This side they have applied some adhesives here. Okay, then they have coated a little bit thicker layer of ITO. Okay, on this side. Okay, then right next to that they have got one more layer, that is nickel oxide layer here. Nickel oxide layer is there at 0.5 micrometer, and this side it is tungsten oxide. Okay, WO3 layer is there. In between, electrolyte is there, tantalum oxide or something. That is 5.5 micrometer film. Okay, so this is outdoor side and this is indoor side. This is the construction. You have to draw this diagram. Okay, so how it works? Device shows light modulation by applying DC potential between the two ITO films. Coloration is achieved by applying 1.5 volt to the ITO of the nickel oxide side. Okay, when you apply this side, okay, when you apply voltage on this side, okay, what happens? The coloration takes place, right? Coloration is achieved. Okay, how much voltage you are applying? Just 1.5 volt, or dry cell voltage. And if you want to reverse, you want the color to be removed, bleaching action to be taken, then you have to reverse the potential. You make this as cathode now. Earlier you have made nickel oxide as an anode. Now you make it as cathode. The reversal of potential shows bleaching. When a potential is applied across the two ITOs, electron transportation takes place. Okay, to the tungsten oxide. So simultaneously, a cation M plus is injected from the electrolyte. Electrolyte, the tantalum ion or something that comes out. So here, lithium usually they use. Okay, here tungsten oxide, which is clear. Okay, and it takes electron coming from where? Nickel oxide side. Okay, and it reacts with the metal ions coming from the electrolyte. The electrolyte may be H plus ions may be there. Okay, lithium tantalate, or it may be tangenic acid also, H. Okay, H or lithium we have mentioned. Okay, MX, tungsten oxide. Okay, hydrogen maybe H2WO3 or something, whatever it is. Okay, which is deep blue in color. Okay, when you supply electrons, so where from these electrons are coming? These electrons are coming from nickel oxide side. Okay, you have made that as anode. Okay, this defines WO3 as cathodic electrochromic material. Consequently, reduction of tungstate occurs. Okay, color changes from clear to deep blue. Okay, this is given in this equation. This is the equation how it works. Okay, this is working I'm discussing. So what happens to counter electrode? Okay, nickel oxide is oxidized due to the insertion of OH minus ions. Okay, extraction of electron as depicted. Okay, nickel oxide has to give electrons. When I say it as anode, it has to give electrons. Okay, oxidation. It has to undergo oxidation, and tungsten oxide has to undergo reduction. Okay, so this undergoes oxidation. Okay, reacting with OH minus ions. Okay, nickel hydroxide, which is a gray material, and you get electrons. These electrons migrate to tungsten oxide, and they react. They take this metal ion, that metal ion or H plus ion from the electrolyte, and they form a deep blue colored metal tungstate or tungstic acid. Okay, this device bleaches by changing the polarity of applied potential. If you make this nickel oxide as cathode and tungsten oxide as anode, bleaching effect takes place. Ion transfer occurs between the two electrochromic materials via the electrolyte. Hope it is clear to you. It's not that rocket science to understand this simple thing. Okay, so this is how. Okay, FIB, focused ion beam. They have, they have observed observation of cross cut section by focused ion beam. Focused ion beam is nothing but your SEM, TEM or something. Okay, right here. This layer is ITO layer. Okay, this layer is ITO. This these two. This is your tungsten oxide, and this is electrolyte, and this here it is nickel oxide, and then ITO, then glass. Okay, this is glass again. This is how it works. Okay, so if you see the spectra, okay, transmittance you see in the bleached state, it transmits some what percentage of light? 80% of visible light. You see, visible light. This is visible range. Okay, even it transmits the infrared light. See, visible light. Okay, it's transmitted here. 80% is transmitted. In the colored, okay, coloring effect. Okay, when it is colored, it transmits only how much? This much light. Okay, only 20% or less light is transmitted if it is colored. Okay, this is how it works. Okay, another example of electrochromic window. Okay, another example, we can use polyaniline, Prussian blue, which is a dye. Okay, and tungsten oxide. Okay, we can use tungsten oxide, Prussian blue. Instead of nickel oxide, we can use polyaniline. Okay, which is, you know what is polyaniline? Polyaniline is a conducting polymer. Okay, Prussian blue is a dye. Okay, so indium root ITO is used as transparent conducting oxide conductor. As an ionic conductor, we have made use of what they have used is solid state polymer proton conducting electrolyte, that is poly 2-acrylamido, okay, 2-methyl propane sulfonic acid. Okay, any sulfonic acids. Okay, right. PAM, PS they call. Or you have studied Nephyon, okay, proton exchange membrane, that can also be used. Okay, the total electrochromic glass sandwich may be then written as, the construction is two glass. Okay, inside it is coated with ITO because you have to make it conducting. One side anode polyaniline and Prussian blue is there, a dye, and then this is electrolyte. Okay, conducting polymer. Okay, here it is proton exchange membrane. Okay, electrolytes. Okay, and tungsten oxide again it is a cathodic material. There are so many examples are there. Okay, research every day, new material comes. Okay, they are working on this, which is typically able to regulate as much as 50% of total solar light. This example, they have demonstrated that it can reduce 50% of total solar energy. The transmission regulation of window-based polyaniline, Prussian blue, and tungsten oxide is also they are shown in this figure. Okay, they have applied the voltage glass. Okay, two glasses. Okay, ITO here, indium protein oxide, and then we have polyaniline. Then we have Prussian blue, the dye. Here, tungsten oxide, WO3, and ITO again on the glass. This PAMPS is electrolyte. Okay, the construction is same. Only thing, some materials are different this side. Okay, this side materials are same. So you can regulate this. What they, if you change the voltage, okay, if you change the voltage, you can regulate the how much light to enter inside the building. This is what, see, if you apply 1800 millivolt, 0 millivolt, 200 millivolt, so you can vary the light intensity, the light entering the building. So this is about switching glasses. It's one of the best discoveries nowadays. Okay, most of the green buildings are using this switching glasses. Okay, I'll stop here. Other things I'll take it up in the next class. If you have any questions, you can ask me. Okay, and I don't think it's that difficult to understand. Okay, so if you have any questions on switching glasses, you can ask me. Yes, if you don't have any questions, just type your name and USN. Okay, so next Tuesday we'll meet. We'll conduct the second OBA the same time. Okay, 10:50 to 11:50. Okay, we'll complete that OBA. Okay, come prepared. Okay, and you need to submit the right the OBA open book assignments. Okay, when the college opens. Okay, right, you upload this now. Okay, but you have to keep that. Okay, both the assignments, or if you have that pink book, you write it in that book only and scan it and upload it if you have it. If you don't have it, you just write it in white pages, and finally you have to take that cover page of that pink book, that assignment book, and attach it. Okay, bind it. Okay, and submit it. Right. So we'll stop here. We'll take up the other things in the on Wednesday. Tuesday we'll conduct OBA. Right. Okay then.